Ladies and gentlemen, good day. We're going to continue with Chapter 11 on our course in Heat and Mass Transfer, Chapter 11 on heat exchangers. The textbook we are using is the textbook of Cengel and Ghajar. We've done the theory of the effectiveness NTU method, and we are going to do an application now. An example. This example is given as a tube-in-tube heat exchanger. We've got water at 20 degrees Celsius with a mass flow rate of 1.2 kilograms per second, and it is being heated to 80 degrees Celsius. We've got brine. What is brine? Brine is salt water, typically geothermal heat, which is being used at a temperature of 160, the mass flow rate of 2 kilograms per second. Most probably this pressure is quite high, otherwise it will be boiling at this temperature, or it might be boiling. The tube's diameter is 15 millimeter. It's given that it is a thin tube, and the overall heat transfer coefficient of the heat exchanger is given as 640 watts per square meter Kelvin. And they ask us to determine the length of the tube on the inside. If you look at this, you'll see that because the mass flow rate is given, you can get the heat transfer rate of this stream. You can equate it to that, and then you can actually get this outlet temperature, and you can solve this problem with the LMTD method. But we are not going to use the LMTD method. We are going to use the effectiveness NTU method. Right, with that method, we calculate the heat capacity rate on the hot side, which is the mass flow rate on the hot side multiplied by Cp on the hot side. And the mass flow rate is 2, and the Cp value is 4.31 multiplied by 10 to the 3, and that is equal to 8,620 watts per Kelvin. That is then for the hot stream. For the cold stream, we do exactly the same. The mass flow rate on the cold side, the Cp on the cold side is 1.2 is the mass flow rate. The Cp is equal to 4180, and that is equal to 5,020 watts per Kelvin. The next step is to calculate C minimum. C minimum is just the smallest of the two. The smallest of the two is, of course, this one, is 5,020 watts per Kelvin. Why do we need to get C minimum? Because we need to get C, which is the ratio of C minimum divided by C maximum. C minimum would then be 5,020. C maximum would be 8,620, and that would be equal to 0.582. One of the very important characteristics of the effectiveness NTU method is to realize that if that is the maximum inlet temperature, and that is the maximum inlet temperature, then the maximum delta T is those two extreme values. You see that? So that heat exchanger can never produce more heat transfer rate than that using that delta T. So Qmax is then always equal to C minimum multiplied by the hot in temperature minus the cold inlet temperature, which is delta T max. Is C minimum multiplied by delta T max, and that is equal to 5,020 multiplied by 160 minus 20, and that is 102.8 kilowatts. Why do we use C minimum there? Because we've previously showed that the stream with the lowest C minimum will have the largest temperature difference, the largest temperature change. Okay, so this is the maximum heat transfer rate that you'll be able to get out of this heat exchanger with these two temperatures. Doesn't matter how long you're going to make it. Okay, now the real heat transfer rate, we can see it from the cold side, is equal to the mass flow rate of the cold side multiplied by the outlet temperature of the cold side minus the inlet temperature of the cold side. The mass flow rate of the cold side is 1.2. The temperature out is 80. The temperature in is 20. And the result is a heat transfer rate of 301 kilowatts. The effectiveness is then the heat transfer rate by Q max. So the heat transfer rate will be 301 kilowatts with these two temperatures and with that mass flow rate. So the effectiveness is then equal to 301 divided by 702.8, and that is equal to 0.428. So we have two things which are important. We've got C and we've got the effectiveness. Why is that important? Because if we go and look onto the graphs that has been now developed from theory and the tables, then firstly you can see for a counterflow heat exchanger, can you see this long formula? You can go and calculate the effectiveness if you've got NTU and the C value. Now in our case we've got the effectiveness value and the C value. So from that equation you'll be able to calculate the NTUs. See that? Now you would say, well, that's now a little bit, why did they write it like that? I would have liked it if it's in the other format. There's it in the other format, in the other table. So in that table you get the NTUs as a function of the effectiveness and the C. Okay, so if you want it exactly, accurately, then you're going to calculate it from that table. Or if you're maybe busy with the first design iteration and you typically would like to have order of magnitude values, then you can get it from this curve, because there's the effectiveness, there's the NTUs, and there's the C values. Okay. So the curve does that. There's the effectiveness values, there's the NTU values for different values of C. Now in our case we've got the effectiveness, which is 0.428. 0.428. We need to get that line where C is equal to 0.582. Of course you cannot get it very accurately from the curve, but from it you can get the NTUs then is equal to 0.651. Obviously getting a value of 0.651, you're only going to get that if you do the calculations. Okay? Now, the NTUs by definition is equal to overall heat transfer coefficient multiplied by the surface area divided by C minimum. The NTUs is equal to 0.651. It's equal to the overall heat transfer coefficient, which has been given as 640. The tube diameter is pi multiplied by the diameter, which is 15 millimeters. It has been given as 15 millimeters. We do not know the length. That is what we need. Divided by C minimum, it's 5,020. And from this we can calculate that the length of this counterflow tube-in-tube heat exchanger must be 108 meters. Okay, are you happy with that? Okay. Now, it's a calculation and there's a value. It is easy to calculate things. But just go and try to think now of a heat exchanger of 15 millimeters. It's going to be an annulus. They didn't give us that value, but you can go and calculate it. Most probably about 50 millimeters or something like that, but with a length of 108 meters. It is an uncomfortable thing. If you must get it into this building, 108 meters, you can't bend it. Obviously, you can get it while you're busy with construction. You can put it in, but if you need to replace it, it's a very long thing, not something very nice to work with. So typically, these types of lengths would obviously not be practical if you want this type of heat transfer with these types of innate temperatures and mass flow rates. You'd rather go for a shell and tube heat exchanger or a plate heat exchanger, which will be much more compact. Okay. Let's do a second example. In this example, we've got actually a shell and tube heat exchanger. And I'm just going to draw it schematically. In this case, we've got oil, the temperature of 150 degrees Celsius, mass flow rate of 0.3 kilograms per second, and a CP value of 2.13 kilojoules per kilogram degree Celsius. And it is a one shell pass and an 8 tube pass heat exchanger. This is now the tubes, 1, 2, 3, 4, 5, 6, 7, and 8. Going in and out. The tube diameter is 14, thin tube. The overall heat transfer coefficient, U, is 310 watts per square meter Kelvin. We have water flowing in, the temperature of 20 degrees Celsius, and a mass flow rate of 0.2 kilograms per second. And the CP of the water is 4.18 kilojoules per kilogram. Okay. I'm going to repeat all the values just now for you, in case you can't read it, and in case it's too close to each other. Okay. Let's start. Oil, 150 degrees Celsius, mass flow rate 0.3 kilograms per second, and the CP is 2.13 kilojoules per kilogram degree Celsius. Everybody's got it? Water at 20 degrees Celsius, mass flow rate of 0.2 kilograms per second, and CP 4.18 kilojoules per kilogram. Okay. The overall heat transfer coefficient of the tube is 310 watts per square meter Kelvin. The tube diameter is 14 millimeters, and one of the tube lengths, each of the tube lengths is 5 meters, each one of them. And the question would be, let's determine the heat transfer rate and the outlet temperatures of the oil and the water. Okay, now this is a good example of a problem where you only have the innate conditions. The heat exchanger is a known heat exchanger, but you don't have the two outlet temperatures. If you don't have the two outlet temperatures, you cannot calculate the LMTD. You can select one, so you can iterate it, but it takes a long time to converge, and that is really why we've got the effectiveness NTU method. It is ideal for this type of problem. Again, let's calculate the capacity ratios of the two streams, the mass flow rate on the hot side, the CP on the hot side. The hot side is 0.3 kilograms per second, and the CP is 2130, and the result is a value of 639 watts per Kelvin. The cold side, the mass flow rate on the cold side, the CP on the cold side, 0.2 multiplied by 4180 is equal to 836 watts per Kelvin. Take note, this was in kilojoules per kilogram. Here it is written in terms of the total value of 4,180 and 2,130. Right, so now we can say C is equal to C minimum divided by C maximum. The smallest one is 639. The largest one is 836, and that will give us a value of 0.764. Q max would be equal to C minimum multiplied by delta T max. Let's draw the two temperatures here. We've got on the hot side 150. On the cold side we have 20. Outside, okay, like that. So if we look at this, the maximum temperature difference is those two values, delta T max. Smallest C value is 639. Delta T max would be 150 minus 20. And that is equal to 83.1 kilowatts. Okay, so that heat exchanger with those two temperatures, obviously with that mass flow rate given and the specific streams, it can never produce more than 83 kilowatts. We are going to use the surface area later on, so let's calculate it. The surface area of the tubes is equal to pi multiplied by 14 millimeters, and they are 5 meters in length. Okay, you happy with it? Good. Remember, there are 8 of them. This is an 8-tube pass. The length of every tube is 5 meters. So, number of tubes. The number of tubes, we need to take that into consideration. 1.76 square meters. We need this because we can then use it to calculate the NTUs equal to the overall heat transfer coefficient multiplied by the surface area divided by C minimum. The overall heat transfer coefficient is equal to 310 multiplied by the surface area 1.76 divided by C minimum, and C minimum is equal to 639. And that is an NTU value of 0.854. I hope you remember an 0.854 value would tell you that there are actually this heat exchanger, there are potential to really improve its performance significantly by just increasing the surface area. Typically order of magnitude 1.52, from there on you wouldn't like to do it. But in this case, from this, it should be clear. Right, so what do we have for this heat exchanger? We've got the NTUs and we've got C. Okay, so let's go and look in our graphs and in the tables. Okay. The first table is this one here, table 11.4. It says shell and tube heat exchanger, a 1 shell pass and 2, 4, 6 and 8 tube passes. Do you see? Okay. So you'll be able to use this equation because you've got C and you've got the NTUs, and you can go and calculate the effectiveness. Okay? Especially if you now want to be accurate. Because I'm lazy, of course, I would like to rather use one of these. And this is a shell and tube one. Unfortunately, I think you can't see the rest here in terms of what it is valid for, but I think this one, let me just see. Yeah, I think this one is valid for 2, 4, 6 and 8 tubes. So here you've got the NTUs, and there you've got the C value. So from that curve, you'll be able to get the effectiveness. Okay, so the curve is like that. The NTUs, for different values of C. We've got NTU, an NTU value of 0.854. Okay, we need to get the line for which C is equal to 0.764. Of course, you won't be able to get it that accurately, and from there you can get the effectiveness of the heat exchanger is equal to 0.47. Obviously, I'm lying. I didn't get it from the graph. I got it from the calculation. But if you do the calculation, always just go and check on the graph if you're approximately in the right ballpark. Right, now that we've got the effectiveness, we can say it is equal to Q divided by Q max. And we've already calculated Q max, there it is. So from that we can calculate that the heat transfer rate must be 39.1 kilowatts. Okay, so the first part of the question has been answered. What is the heat transfer rate? Now we need to get the outlet temperatures, and that is very simple because we can say that the heat transfer rate on the hot side is equal to Cp on the hot side multiplied by the mass flow rate, of course. The mass flow rate on the hot side, the Cp on the hot side, inlet temperature hot, the outlet temperature hot. The heat transfer rate is 39.1 kilowatts. The mass flow rate on the hot side is 0.3. Cp value is 2130. The inlet temperature on the hot side is 150. The outlet temperature on the hot side we want to determine. That's the only unknown, so we can determine the outlet temperature as 88.8 degrees Celsius. You all with me? I'm not going too quickly. Okay. So the next one is, now we do it on the cold side. The heat transfer rate on the cold side is equal to the mass flow rate on the cold side, the Cp on the cold side, the outlet temperature on the cold side minus the inlet temperature on the cold side. The heat transfer rate on the hot side and the cold side, both of them must be 39.1 kilowatts. is equal to the mass flow rate is equal to 0.2. Cp is 4180. The outlet temperature we want to determine, the inlet temperature was 20, from which we can calculate the outlet temperature as 66.8 degrees Celsius. Okay? You've got it? Okay. Now, as I've mentioned, this effectiveness or this NTU method tells me that there's actually lots of potential to improve this heat exchanger. So let's suppose you would like to make a design modification, for example, going to a 2-shell pass and a 16-tube pass heat exchanger. Okay. So let's suppose there's not a lot of room in the shell, and you can use a second shell with the same number of tubes. So now it becomes a 2-shell pass and a 16-tube pass heat exchanger. The thing that will change is the number of transfer units, because the length of the tubes, where previously you had 8, now becomes 16. So the surface area increases, okay, to 2 times 0.854, which is equal to 1.7. If you now get the effectiveness will increase to 65%, and the heat transfer rate would improve to 54 kilowatts. By just making a small modification, and that would increase actually the heat transfer rate by almost 40%. Ladies and gentlemen, any questions? If not, thank you very much, Tamron. You can cut.